Hey everyone, it's Miss Butler. I got our first set of notes for gas laws, where our ultimate goal of this unit is to quantitatively, so calculations, and qualitatively, so just thinking about what's actually happening to the particles, look at the relationship between volume, temperature, and pressure of gases. So this first video, you are going to take notes in your Cornell notes. It's on kinetic molecular theory and pressure. So, kinetic molecular theory is what we use to describe how gases behave, and there are some different bullet points that are associated with the kinetic molecular theory. So, we are going to assume that gas particles do not attract or repel each other. Gas particles are small, so they don't count towards the volume. We just really look at the volume of the container, not the volume of the individual particles. Gas particles are in constant random motion. You should have seen that with the simulation. They are randomly moving around and they never stop moving, and part of that randomness I feel like is associated here, that they don't attract or repel each other, so they just keep randomly moving until they hit a container or they hit another particle, and then they bounce off. They don't stick together with other gas particles when they collide. When they do collide with other particles randomly, or the sides of the container randomly, kinetic energy is transferred. And then all gases have the same average kinetic energy, which is speed at a given temperature. So basically what I'm saying here is that temperature is the same as average kinetic energy for gas particles, which is going to be associated with speed, how fast they're moving. All right, so the first variable that we are going to look at for gases is called pressure. And the definition of pressure is how hard and how often. So how hard and how often the gas particles collide with the walls of the container they are in. So when we're measuring pressure, that's going to depend on two things. It's going to depend on the force that the particles are using when they collide. Are they gently ping, ping, or are they aggressively boom, 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 ramming to the side of the container? And the amount of area or space the particles have to move around, right? If I have a box this big versus this big, there's going to be more potential for collisions in a smaller box like this, right? Look at how often it's colliding, versus here it's not colliding as often. So if we were to measure pressure, we'd be looking at the force divided by the area. That's again kind of essentially taking the definition of pressure and putting it into like a quote unquote equation. One of the tricky things with pressure is that it's not always measured with the same unit. Kind of like we will measure distance sometimes with miles or kilometers or inches or centimeters, right? You can measure the distance between 2 points with lots of different units. Pressure is the same way. So here are the units for pressure: atmospheres, and it's abbreviated ATM; kilopascals, which is lowercase k, capital P, lowercase a, kPa; millimeters of mercury, mmHg. Sorry if that's hard to read in yellow. I wrote it next to it just in case. Inches of mercury, INHg; torr, TORR; and pounds per square inch, PSI, which is maybe more familiar to you for your tire pressure or basketball pressure. Things like that are usually in PSI. Okay, I'm going to attempt to show you these two very short videos. I did another video for a different class where I played the YouTube videos and it didn't pop up. It was just like silent for the entire time. So if that is the case, I posted both of these on Canvas on the calendar. Please watch them. So pause this video, pull these guys up for me just in a different tab or something. I'm sorry if they don't play. I will try to play them in this video, but I'm not sure if it's going to work. All right, let's see if this works. Otherwise, you're going to click on the first video link on Canvas on the calendar.
In the days before scuba, if you wanted to descend into the deep, suits like these were your only option. But according to this myth, they came with a deadly drawback. So to put the squeeze on this deep sea saga...
All right, let's get some meat on these bones.
Tori, Grant, and Jesse are turning up the pressure.
All right, camera mounts, check. Diving helmet mounts, check.
300-foot umbilical, check. Dive suit, check. Helmet, check.
And finally, Meat Man is done. Now it's time to take all these things out to the ocean, take them down 300 feet, and find out whether or not Meat Man will get the squeeze.
So to do that, it's off to Santa Cruz Harbor, where the experts from North Coast Divers will take them out to sea.
And Meat Man is in the water.
Bye-bye, Meat Man. Say hello to Davy Jones.
As they monitor his slow descent, the team is skeptical of a full-body squeeze.
I honestly think that there's going to be some juices flowing, but I don't think it's going to suck the skin off his bones.
I don't think it's going to happen immediately. I think it's going to be fairly slow because there's 300 feet of line that the air has to exhaust through. I don't think the whole body's going to come up. I mean, there's a lot of meat down there. I don't think all of that's going to come in the helmet.
Okay, that's 300 feet. Okay, stop the cage.
At that depth, there's 135 pounds of water pressure pressing on every square inch of the diving suit. The only thing keeping the water at bay is the compressed air. So will cutting the air supply lead to a spectacular squeeze? There's only one way to find out. This season.
All right, so hopefully that played for you. So before we watch the next clip, in your Cornell notes, you should have room to make a prediction. What will happen to Meat Man when they cut the compressed air inside the suit? So write that down. Okay, during this video clip, I want you to record your observations of what you see happening to Meat Man when they cut off the air compression in his suit. Again, I hope this plays. If not, if you can't see anything or it's all quiet, you can pull up this link on Canvas.
Yeah. Ready in 3, 2, 1.
The effect of the cut hose was less than instantaneous. But once the air pressure was exhausted, physics took over, and the drastic pressure differential pushed Meat Man into his helmet, exactly as the myth predicted.
I don't even think we need to bring him up.
No!
Just leave him down there.
Wow!
Look at that.
That was
Look
gonna
at those
happen.
side glasses. Look at
That's
that.
amazing.
You can't even see in the helmet anymore because it's covered with flesh and blood. Who's going to clean the suit?
Not it.
And a closer inspection of our diver reveals the kind of damage 135 pounds of pressure per square inch can do.
Oh, wow!
Oh my God! Stop! We totally caved the helmet in!
Look at all the guts in there.
His stomach is inside his helmet.
Just by the side of the helmet. Look at that.
Dude,
Could you imagine that pressure?
that is absolutely confirmed. No doubt about it.
Totally confirmed. Okay, so I definitely expected the juices to be flowing, but I didn't expect to see them like slowly rise up through the helmet. And then blah, where everything just, it was like an explosion inside the suit. Completely unexpected, but totally awesome.
Now, the name of this game is differential pressure. They can withstand a huge amount of pressure when they're equalized. But the second you take away all the pressure on the inside, crush. You can see, this is what's left.
I saw it with my own eyes. I still can't believe this actually happened. This one is completely confirmed.
I'm sorry, Meat Man, but it was totally worth it.
You guys are...
All right, again, I hope you can see that video. Otherwise, thanks for pulling it up on your own. So let's talk about what they were talking about in this video, internal pressure versus external pressure. So I got my Meat Man in the water. And water, similar to gases, water has lots and lots of pressure. In fact, what they said is the water at the depth that he was at was pushing on the Meat Man suit with 135 pounds per square inch, PSI. So that means the Meat Man essentially was feeling pressure of 135 pounds, like sitting on every square inch of his body. So obviously, when they first put him down into the water, nothing was happening. So what that means, so this is outside the body, I'm talking about external pressure. But then when they first put him in the water, nothing was happening. He was just chilling down there because his suit was connected to a air compressor, which means there must have been 135 psi pushing outwards, right, to balance it out so nothing terrible happened. So in this case, my P internal was equal to my P external. What happened though when they cut the pressure? Well, there was still 135 psi, right? He didn't change depths in the water. There was still 135 external pressure pushing on Meat Man in every square inch, right? So my external pressure was 135, but my P internal dropped, right? I don't know how much it dropped. They just cut it off entirely. So let's just say it dropped significantly. Well, what's going to happen if my P internal is less than my P external? What's going to happen? Well, my pressure on the outside is going to start to squeeze and push, which eventually caused Meat Man to crush, and then all the meat went kind of up in the sturdier helmet. But even you saw the metal helmet even crushed itself. Okay, so a lot of things in gas laws is going to be a battle of internal pressure versus external pressure. And usually if the external is larger than the internal, we're going to see implosions happening. If the external is less than the internal, that's where we get explosions happening. So how do we actually measure pressure? There's two different tools we may use. One is called a barometer, and that's usually what's used in weather reports. So essentially you have this mercury that's sitting right at the bottom here, and the atmospheric pressure, so the gas particles are colliding, right? We're measuring how many collisions there are, and they're colliding with this liquid, which forces it up the channel, and then I can measure and record what the atmospheric pressure is. A manometer is used to measure the pressure of other gases compared to the air pressure. So I have some sort of vacuum, I open it up, I can see what is the pressure of this gas in here, and what is this pressure. And I'm going to show you how to use a manometer and how to measure it in the next slide. If my example is not enough in the next slide and you need more, I have put this in your Cornell notes as well. An older chemistry teacher from Legend that I used to work with made some videos as well. So you can watch this video link from 0 to 150. She goes through how to also read a manometer. Okay, so this problem says determine the pressure of CH4 if the atmospheric pressure is 750. So here's how it works. This is sealed. Here's my CH4. I don't know the pressure inside that bulb, and this part is open to the atmosphere, and this guy right here is 750 mmHg. So they must have used a barometer, and they know the pressure of the atmosphere that's going in this tube. Look at these black bars. I want you to picture a small child jumping up and down, up and down, up and down, and a small child jumping right here. Looking at those small children, who is jumping harder, A or B? Well, to me, it looks like child A is jumping harder because this black bar is getting pushed down lower and this bar is being pushed up, right? If it were the other way around, the black bar maybe would be down here. So I'm going to say that the atmosphere on this side with child A is my winner, which means the CH4, the one that's not jumping as hard, is my loser. Occasionally, problems will give you numbers, a number here and a number here, because I want to know how much is the winner winning by, right? So I can figure out that by doing a subtraction to find the difference, right? So I'm going to subtract those given numbers to figure out the difference. So first of all, it's not always the highest number. Sometimes they'll make this 100 and this one 70. Notice 70 is a lower number, but that side with A is actually my winner, right? So always look at that black bar of mercury to figure out who's my winner and who's my loser. So this is mercury in here, and the one that's pushing down harder is the winner, okay? To find the difference, we're going to subtract big number, 100, minus small number, to get the difference, 30 mmHg is the difference. So that's already marked for us on here, but I just wanted to show you how to do it if they gave you the numbers like 170. So what this means is that the winner wins by 30 mmHg, or 30 points. So what side's my winner? Well, my winner right now scored 750 points, 750 mmHg. My loser then will have a difference of 30 points. Well, what's the score? Well, my loser can never score more points than my winner. So if my winner had 750 points and my loser lost by 30, that means my loser had to score 720 points. So this guy right here must be 720 mmHg. Notice, I made my winner blue and my loser red. Why? Because I'm a biased individual and Legend always wins, right? So Legend is my winner on this one and Shap is always my loser. And sometimes your winner is the CH4, or the unknown gas, and sometimes your winner is the atmosphere. But the important thing to check is, think of it like sports. Legend is always your winner with the higher score. So because the CH4 represented Chaparral, it had to have less points. If we had added 30, it would have been 780 points, and that doesn't make sense. Legend wouldn't have won if Shap scored 780. So in this case, my answer is 720 mmHg. When this video is over, you're going to go into Canvas, and there's Manometer practice problems. It's actually these 6, but you won't get all 6 of them. They'll be pretty randomized for you. But you're going to practice those. You can do multiple attempts, but let's make sure you can figure this out. Notice all of them, you have to calculate the difference. So you have to figure out, oh, this side's jumping harder. He's my winner. Let's make it the correct color. So my loser is here, and then you'll find the difference to figure out how much the winner won by, okay? Email me if you have questions. If you try one attempt and you're confused, email me and I'll help you out. All right, last thing we're going to talk about is atmospheric pressure. Is the atmospheric pressure the same everywhere on Earth? I'm going to argue no. If you look on this graph, here's sea level. They're saying the average pressure is 760 mmHg. What happens then as we go higher and higher up? At Everest, the pressure is 750 mmHg. So this is a common misconception that kids get confused, right? You know that in Colorado it's harder to breathe. People come visit, they have trouble breathing. But that is because when you go higher in altitude, you actually have lower pressure. Here's why. In Colorado, there is less oxygen. Have you heard them say that the air is thin? What that means is there are less particles in the air in Colorado. So if these particles are bouncing all over the place, and pressure is how they collide with the container, right? Well, if you have less particles in the box, there's going to be less collisions, right? With less particles, there's less collisions. People say the air is thinner, and that results in lower pressure. So in Colorado, we are at a higher altitude. There's less oxygen. The air is thinner. There's less collisions of the gas particles, which means there's a lower pressure, which is exactly why Olympic athletes train in Colorado Springs, because what they're trying to do is train their lungs to be used to having less collisions while they're exercising. Here's just some interesting facts, I think, related to Colorado and adjusting to the high altitude. So how does our body actually adjust? Well, when you're adjusting, you want lower PO2, which is lower hemoglobin saturation. So what we're trying to do is our bodies breathe deeper, which increases the red blood cells and hemoglobin. Our heart rate increases, right? And for many people, it can take 2 days or up to a week to adapt. And there's different levels. I'm sure you've heard of altitude sickness before, but there are different levels. So acute mountain sickness is usually about 8,000 feet, but it can occur lower if people are sensitive. And usually people will feel like they have the flu or hangover, kind of headache, kind of cloudy thoughts. High altitude pulmonary edema is anything usually above 8,200 feet, which is more trouble breathing, wheezing, hard, like your chest feels tight, can be fatal if you don't adjust and go to lower altitude. And high altitude cerebral edema is at 26,000 feet, and this can cause swelling in the brain. Most people cannot climb this high without an oxygen tank. So just kind of some things that those daredevil climbers of Everest are thinking about as they climb higher and higher to the summit. Hopefully that was interesting for you. Let me know if you guys have any questions. You're going to work on the manometer practice problems on Canvas.